Hey class, this is Adrian again. I wanted to go ahead and make a video here for section 4.2, which talks about the unit circle. We're actually going to define our trigonometric functions, sine, cosine, tangent, etc., using this unit circle definition. I'm not going to go into too much detail. Last video I made was quite a bit longer than I intended. So I did kind of want to just go through this one a little more quickly and just really focus on that section. Again, if you're looking for these handouts, if you go to course content, module 1, chapter 4, handouts and lectures, you will see section 4.2 about the unit circle. And there's various notes. There's some responses I gave to homework questions, etc. But if you open up that PDF handout, this is what you will see. So let's dive right in here to the unit circle. Now, the unit circle is a circle with radius 1 that is centered at the origin of your XY coordinate system. And the equation of the unit circle, if you go back and think about that, is this equation: x squared plus y squared equals 1, right? And if you really want to go to the details, your kind of definition for your circles is x minus h quantity squared plus y minus k quantity squared equals r squared. That's just a generic rectangular equation for a circle that is centered at h comma k. So in this case, we're centered at 0, 0, so h is 0, k is 0, and our radius is 1, so r squared is 1. So anyway, that is your, if you go back to algebra especially, you've probably talked about an equation for circles. That is the equation for the unit circle. Now, if you could think back to last section, we talked about arc length. We talked about how radian measure, right, theta equals S over R, where S is your arc length and R is the radius of your circle. So for the unit circle at least, and we solved this last section, we said, all right, if I multiply both sides by R, I get the equation S equals R theta. Well, for the unit circle, your radius is 1. So S is equal to theta. So that's kind of a unique feature of the unit circle, is that the arc length of any point that you pick on here, if I look at this arc length, it's going to be exactly the same as the radian measure of that angle that creates that arc length. So kind of interesting. Now the next part of this, what we really want to do is we want to define really 2 or 3 trigonometric functions, and they're going to give rise to 3 other trigonometric functions. And one of those is sine of theta. So you see sin theta, and theta, a lot of times your angles are Greek letters. So in this case, sine of theta, y equals r sine theta. Now notice the r is kind of small here, and as you look down here at all these definitions, kind of small. And the reason r is small here, and I don't point it out too much, is that r is 1 on the unit circle. So I'm going to let my y coordinate essentially be equal to the sine of theta. And I'm going to define my x coordinate the same as cosine of theta. And if you wanted to look out, what's the tangent of theta? Well, I'm going to define that as y over x. So the ratio of what my y coordinate is to my x coordinate. And this is for points on the unit circle. And cosecant, secant, and cotangent, they are really just the reverse. They are the flipped version of that. So if this is y, and I take 1 over that, that is cosecant of theta. If I take 1 over x, then I'm getting the secant of theta. And y over x, if I flip that, I get x over y, and that's my cotangent of theta. So what this allows us to do, and this is just one of the definitions of trigonometric functions, is just based on unit circle. So for any point on the unit circle, I can use these definitions to define and tell me what the functions are. So when I look here and I say, all right, here's my angle theta. I don't know what the angle is in degrees of radians, but I do know that on the unit circle at least, here is the point that would be represented at that angle. And I could say, well, the sine of theta would be the y coordinate of that point, right? So the y coordinate here, again, this is x comma y, is going to be 1/2. So that would be the sine of that angle. The cosine, again, that is x. So I would come in here and say, well, that's going to be square root of 3 over 2. So that's two of my functions are defined. And we'll find out that we can really use those two to define everything else in here. But as I come in and say, all right, tangent of theta, that is y over x. So in our case, that would be 1/2 divided by the square root of 3 over 2, right? That's your y, that's your x. So kind of go back to algebra and we say, well, okay, I need to simplify that down a little bit. So when you're dividing fractions, you want to take your top fraction 1/2 and you multiply by the reciprocal of the bottom. So I'm going to flip the bottom, so times 2 over square root of 3. Okay, well, the 2's cancel when I do that multiplication, and I get 1 over square root of 3. Now that looks good. It's not a bad, it's kind of a correct answer, but we can simplify that a little further, and you're going to see that in the homework. They are going to ask you to simplify that. In particular, they don't like to see those radical signs in the denominator. So the way you rationalize the denominator, get rid of that, is I can say, well, I have this point, right? 1 over square root of 3. So if I want to get rid of a square root, if I multiply by the square root of the exact same thing, then I'm going to get rid of that. Square root of 3 times the square root of 3 is the same as the square root of 3 squared, meaning the square root is gone, right? So square root of 3 times square root of 3, another way of thinking that would be the square root of 9, which is my 3. So you're effectively removing it from the radical sign. Now when I do that though, if I multiply by square root of 3 over here in the denominator, then I also have to multiply the numerator by that, right? Otherwise I'm not multiplying by 1, I'm actually changing the value. So if I do that, I get square root of 3 over 3. So that is the answer in the homework and on quizzes and stuff that I am looking for, at least in this case, for tangent. Okay, so sine, cosine, tangent. Now the other three, cosecant, secant, and cotangent, we're just going to flip those to get those results. So the reciprocal here, if I take 1 over 1/2, is just 2 over 1 or 2. So as I look at the secant, I'm going to flip my cosine. So I'm going to have 2 over square root of 3. Okay. So again, I run into that situation where I have a radical sign in the denominator. So I want to get rid of that. So I'll multiply the top and bottom by the square root of 3. When I do that, I get 2 times the square root of 3 divided by 3. Okay, so that's your secant. And we've already got the cosecant. Now, cotangent I find interesting because we could take our tangent, right, and we could flip that. And we could say, well, that would be 3 over square root of 3. Right? And we go through the same process. I'd need to rationalize that denominator. And I would get 3 times the square root of 3 over 3. Well, guess what? The 3's would cancel. And you get square root of 3. So that's the correct answer. Now, a lot of times I'll kind of keep this 1 over square root of 3 over here, right? That's not an answer for tangent. It's not the correct answer. It's not simplified. But if I take that, which is the same, right? These are equal. If I take that version and just flip it to begin with, I get square root of 3 over 1, which is the square root of 3. So you get the same answer either way. Sometimes it's easier to flip that one rather than having to ration. So we rationalized once here and again over here when we did it this way. So anyway, just something to keep in mind. Either way, square root of 3 is cotangent. Okay, so that's kind of your trigonometric functions. We'll do a lot with those as we move on, but this is one definition of how we can use those. Here's another example. This point, p equals 0, comma, -1. So that'd be this point on your circle, right? So it is on the unit circle. So I can just come in and say, well, the sine of theta, given that point, would be the y coordinate. So in this case would be -1. Cosine of theta be the x coordinate, so it'd be 0. Tangent of theta is going to be y over x, so it'd be -1 over 0. Guess what? Does not exist, right? We can't divide by 0. So the tangent for this point, at least, does not exist. We keep going. We could say, all right, the cosecant of theta. I'm going to take the sine of theta and flip it, so I just have 1 over -1. But again, it's just -1. You could keep going. Secant of theta is going to be this cosine flipped. So when it says 0 over 1, effectively, we're going to flip that, and we'd have 1 over 0. So it also does not exist. Okay, so the secant does not exist, and the tangent does not exist. What about the cotangent of theta? Right. Well, if this is negative 1 over 0, I should be using negative 1 here. If this, I'm sorry, got lost there for a second. If this is the tangent, and I take that negative 1 over 0 and I flip it, I get 0 over negative 1. Well, that does exist, right? Because 0 divided by negative 1 is just 0. Okay. So anyway, now we have defined all of our sine, cosine, tangent, cosecant, secant, cotangent, all our trigonometric, base functions for another point on the unit circle. Okay. So this is kind of interesting. If we could pick any point on here and we could say, all right, what's the sine, cosine, tangent given the coordinates of that point? And we can find coordinates, right? We just pick an x value and find the corresponding y value. There's different ways to do that. However, maybe a little more interesting is to think about some of our special angles. So for example, if we go to our unit circle again, I say, all right, let's think about this a little bit. Our unit circle is given here as x squared plus y squared equals 1. Okay. Now, if I take the angle, and I put t here, but you can also use theta. Well, it's just another way of labeling an angle. If I take a pi over 4 angle, right? So that is a 45-degree angle, right? So coming back up here, right, it's got halfway. So at this point on the unit circle, or any circle really, my x and y coordinates are going to be equal. If I'm centered at the origin and I cut that in half directly, then my x is going to equal y. Okay, so if you think about that, the point P equals A comma B, if you think about that, I can come in here and say, well, here's my formula for my unit circle. This has to be true. X squared plus y squared equals 1 for any point on my unit circle. So if I let x be y, if I say, well, those have to be equal, then I could come in here and say, well, let's replace x then with y squared plus y squared equals 1. Well, then I get 2y squared equals 1. Divide both sides by 2, I get y equals 1 half. Sorry, y squared equals 1 half. And then you would take, to find the result here, you would take the plus or minus the square root of both sides. You said, well, y would have to be plus or minus square root of 1 half. Or, simplifying that down a little bit, first off, if I'm at pi over 4 angle, that means I'm in this quadrant, right? So my x and y are going to be positive, at least at that given point. So I don't have to worry about the negative. I also don't have to worry about the square root of negative, or of 1, because that is 1. So I'm going to say square root of 1 is 1. Now on the bottom, I've still got square root of 2. So that's the y coordinate. Obviously, we would want to flip that. So if that's the y coordinate, it's also the x coordinate, right? Because we said x would equal y at this point. So let's simplify that down. Multiply top and bottom by square root of 2 over square root of 2. And we end up with an x and y of square root of 2 over square root of 2 times square root of 2 is 2. So square root of 2 over 2, square root of 2 over 2. So given that, now we know that the sine of a pi over 4 radian angle is going to be the y coordinate, which is just square root of 2 divided by 2. If I said find the cosecant of pi over 4, well, that's sine flipped. If you go back and look, sine is y, cosecant is 1 over that. So it's just flipping that. So the cosecant would be 1, I guess, over square root of 2 over 2. And if you go through this math, you'd say, well, that's going to be equal to 1 times, multiplied by the reciprocal, 2 over square root of 2, which would be 2 over the square root of 2. Again, we're just flipping that. Right? We're taking that square root of 2 over 2 and flipping it. Now, in that case, though, we need to resimplify that. So multiply top and bottom by square root of 2 over 2. Get 2 times square root of 2 over 2. 2's cancel, and you're left with the square root of 2. Okay, so let's come back in here. So, all right, that's the sine of pi over 4. Square root of 2, that is going to be the cosecant of pi over 4. And then finally it says the cosine of pi over 4, which is just going to be the x coordinate, and that is just square root of 2 over 2. Okay. Okay, so that's how you look at those different things. And we could find the others, right? You could find tangent to be y over x, and we'll probably get to that at some point. So that's one way, at least for pi over 4. Now we know another angle. So we could, if you think about your unit circle, you come in here and kind of sketch this out a little bit. It's all right, I have a unit circle here. And we'll say that has, 1, right? So this would be -1. This would be 1. This would be -1. So I have some points here, right? 1, 0, 0, 1, -1, 0, and 0, -1. So those are points all on my unit circle. I could find the sine, cosine, tangent, etc. for all of those points. I can also know now for this point. Now I already know the coordinates of that point, right? They're going to be square root of 2 over 2, comma, square root of 2 over 2. Okay, at a 45 degree or pi over 4 radian angle, I know the sine, cosine is for all of those. So 0 radian, pi over 2 radians, pi radians. I know a few things, right? So far we know between 0 and 2 pi at least. 0, pi over 4, pi halves, pi, 3 pi over 2, and I guess you could say 2 pi, right? Now, we'll figure out a little bit later how we can find some other angles that are in there, but we should know the trig functions for all of those angles now, just based on those coordinates. Now, let's think about something else. Let's think about sine, cosine. What if I wanted to look at whether they're even or odd functions? Well, if you go back to algebra, we probably talked about that a little bit. But really, the way you do that is you evaluate. If you go back, you think, well, f of x, then you have f of negative x. You kind of see what the differences are. So that's kind of the same thing here. If I say, all right, y is sine of theta, right? Y equals sine of theta. What if I take sine of negative theta? So if theta's up here, just some angle up here, for example, this is my x comma y coordinates for my point that's given here. If I take negative that same angle, and you think about it, that's my x coordinate. My x coordinate is not changed, right? It's still at x. It's not changed at all. Now my y, it is a little bit different. Your y coordinate's over here. So if this is y, then this is going to be negative y. And it's the same distance from the origin. It's just in the negative direction. So it would be x comma negative y. Interesting. So in other words, sine of theta is y, then the sine of negative theta is going to be that negative y. Cosine of theta is x. Cosine of negative theta, again, is just positive x. Okay. Now what that means is really cosine, in this case, if you look at this is considered to be an even function. And it's the same thing going to be said for secant functions. In other words, I can rewrite, anytime I see cosine of negative some angle, I can rewrite that as cosine of positive the same angle. They're going to be equal. Now sine, these are considered odd functions. And the reason they're odd is if you go back, right, f of negative x equals negative f of x, right, for an odd function. So in this case, sine of theta is y, so sine of negative theta is the same as negative sine of theta, right? So anytime you see sine of negative, or you see, and it's going to be the same for tangent, same for cosecant, etc. Sine of negative some angle, I can move that effectively move that negative sign out front, make that negative sine of theta. Okay, so that's helpful a little bit if you think about, well, the secant of negative pi over 4, because it's an even function, I would say that's the same as the secant of pi over 4. What is the secant of pi over 4? Well, the cosine was square root of 2 over 2, so it would be 1 over square root of 2 over 2, which is going to be the same as 2 over square root of 2, and we just found that kind of the same thing earlier. So that's going to be, let's just do this here so I don't mess anything up. 2 times square root of 2 over 2. 2's cancel, so I'm just left with square root of 2. So the secant of negative pi over 4 is the same as secant pi over 4, which is square root of 2. Well, the sine of negative pi over 4, now remember this is an odd function, right? So that's going to be the same as negative sine of pi over 4, and we determined that earlier. Sine of pi over 4 is square root of 2, so over 2. So that would be the sine of negative pi over 4. Well, what you could really do is come in here and say, well, now I know this angle. Yeah. I'll make that different because we just kind of picked up on that. This would be a negative pi over 4 angle. If you think of it in terms of standard position, right? This would be 8 pi over 4 if I go all the way around. So if I subtract one of those out, I also now know 7 pi over 4. And you could use similar thinking to really figure out the same thing for all of these angles, right? So pi over 4, 2 pi over 4, 3 pi over 4. You could figure that one out too, right? So in this case, my y value isn't changing. My x value is negative what it was before. So really, we'd also know 3 pi over 4. We also know not 4 pi over 4, which we already said, and then 5 pi over 4. So now we have a variety of angles here that we know should be able to figure out just based on unit circle definition, the sine, cosine, tangent, etc. Okay, so I'm going to introduce you to just a couple of identities, and we'll see these again, especially in the next chapter. But sine of theta is y, cosecant of theta is 1 over y. Well, then what's kind of interesting, if I look at that, well, cosecant of theta is the same as 1 over the sine of theta. So these are really reciprocal identities, and this is kind of common sense, I guess, based on just, your x and y definition. But it's really saying that sine and cosecant are reciprocal functions. Cosine, secant, reciprocal functions, etc. So those are your 6 reciprocal identities, and sine and cosecant, are reciprocals. The other one that you'll see, right, tangent of theta, if you go back, we said that's y over x. Well, y is sine of theta and x is cosine theta. So that one's kind of neat, and we'll see this one again especially, and some of these others. But tangent of theta is sine over cosine. Cotangent is cosine over sine. So those are quotient identities. So what that helps us with sometimes is if I know just these two, then I can find everything else. So in this case, it says sine of theta is 2 over 3, and cosine of theta is square root of 5 over 3. So find the value of the remaining 4 trig functions. So the first one I might want to find is tangent of theta. Well, that's going to be sine divided by cosine. Or in this case, it's going to be 2/3 divided by square root of 5 over 3. Sorry, I wrote that wrong. Well, I want to find this as a reciprocal identity. So I'm going to multiply that now as 2/3 times the reciprocal at the bottom. So it'll be 3 over square root of 5. 3's cancel. I'm left with 2 over square root of 5. And again, I need to simplify that. So I'll multiply top and bottom. Square root of 5. So we're going to get 2 times the square root of 5 over 5. Okay. So that's the tangent of theta. Then I could come in here and say, well, cosecant of theta is going to be 1 over, sine of theta, or it's just going to be that value flipped. So in this case, it'd be 3 over 2. And then finally, secant of theta, or I shouldn't say finally necessarily, but secant of theta is going to be 1 over cosine. So we'll flip that to be 3 over square root of 5. And without going into the detail here on the video, you'd multiply top and bottom square root of 5. So you'd get 3 times the square root of 5 over 5. Again, rationalizing the denominator. And then I guess the last one here, cotangent of theta, I'm going to flip tangent of theta. So again, I could flip this final version, or I could come in here and say, well, somewhere in here I got to this point, right? 2 over square root of 5. If I flip that, I get square root of 5 over 2. So that's your cotangent. And you would get the same thing if you just took this 2 times square root of 5 over 5, flipped that, and then simply rationalized your denominator. You get the same answer. Okay, there's a couple others here that again, we'll talk about these a lot in the next section, or in the next chapter in particular. But these are considered Pythagorean identities. Well, if you go back, our definition was this, right? X squared plus y squared equals 1. Well, guess what? X is cosine of theta and sine of theta is y, so I can replace each of those. Now, cosine of some angle squared a lot of times is written as cosine squared of theta. So these two forms are identical. A lot of times you're going to see it like this, but this is what it really means. So if I know the cosine of theta, if I square that, that's what cosine squared theta is. So anyway, and you could go to some of your other, arrangements up there, y over x, x over y, and you could come up with these other Pythagorean identities. 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared. So those are some other forms you can use, and one way this becomes helpful, and this should already not be a t, that should be a theta. I have sine of theta is 1/2, and I want to know the cosine of theta. Well, notice that 0 to pi over 2 is where my theta has to lie. So it has to be somewhere in that first. I'm looking for an angle somewhere in this quadrant, right? There's your pi over 2, and here's your 0. So I'm looking for some angle here at which the sine of theta is 1/2. Well, that's not a whole lot of information, but if I go to my Pythagorean identity, right? So, well, sine of theta is 1/2. So I could plug that in here. I have 1/2 squared plus cosine squared theta equals 1. Oh, okay. Could keep going with that a little bit. That's the same as 1/4 plus cosine squared theta equals 1. Well, subtract 1/4 from both sides. So I get cosine squared theta equals 1 minus 1/4, so 3/4. So the way you're going to go about solving this, remembering that this is the same as cosine of theta squared, I would take the square root of both sides. And you would typically say, well, then if I take the square root of both sides, we'll get cosine theta over here. And you typically would say, well, that's going to be plus or minus the square root of 3 over 4. But because I know that I'm in this quadrant, my my x coordinate has to be positive. So I don't have to worry about the negative case here. I only have to worry about the positive square root of 3 over 4. And again, we can simplify that. That's the same as the square root of 3. And then I can take that square root on the bottom as 2. So that is the cosine of theta. And I don't know what theta is. I still don't know the angle necessarily, but I know sine of theta and I know cosine of theta. And from there, you could figure out the other trig identity, tangent, cotangent, cosecant, all that kind of stuff. Okay. So the last couple things I wanted to kind of cover here, in particular, was the period of time that these trig functions cover. So if I have a point x comma y on a unit circle, so I'm on the unit circle here. Oh, that's bad drawing. Try that again. Not perfect, I agree. Not great. Okay, so but I'm at some point here, x comma y. So I'll call this my point, x comma y. Now, on that unit circle, if I look at this x and y, right, if I rotate that point, I'm going to be back at that same exact point again when I've gone a complete 360 or 2 pi in rotation. So I know that the period, and that's going to be true for sine and cosine, is going to be 2 pi. So you could think a little bit about these, right? So I would be at the x here, but I wouldn't be at y. I wouldn't be at the same y. If I go down here, I'd say, well, that x or I'm sorry, the x is different, but the y is different too. Here I could say, well, the x is the same, but the y is different between these 2 points. So you could kind of think about this kind of similarly. So here I'm going, I guess 90 degrees around to here. So there's different ways of thinking about this. Most commonly, though, if I want to get back to this exact point, x comma y, then I would have to go 2 pi around. So the period of sine and cosine and secant and cosecant is 2 pi, meaning that's how often those values will start repeating. Now, tangent's a little bit different because this point, if this is x comma y, this is the point negative x comma negative y. Well, tangent's a little bit different, right? Tangent is telling me here I'm at y over x. Well, tangent down here is going to be negative y over negative x. So guess what? That is also y over x. So tangent actually repeats at not a complete circle, but half a circle. So the period of tangent is pi. Now, what makes this kind of interesting is if I'm in sine or cosine, I can always, just kind of like we did with coterminal angles, I can add or subtract 2 pi, or I can add or subtract 360 and get back to a value that I know and I know how to solve. If I'm in tangent or cotangent, then I can add or subtract pi to maybe get back to a value that I know. So these are considered the periods. We'll talk about more of that as we go along. But if you think about that, right, cotangent, for example, of 5 pi over 4. Well, let's think about that one. That should be the same as the cotangent of 5 pi over 4 minus, if I take a pi away from that, I should be at the same value, right? That's my period of tangent and cotangent. So I would be at the cotangent of 5 pi over 4. In common denominators, pi, I would multiply top and bottom by 4, so minus 4 pi over 4, which is the cotangent of pi over 4. Well, we have to think about that a little bit. What is the cotangent of pi over 4? Well, let's go back to kind of where we were defining pi over 4. And we said that the sine was square root of 2 over 2. The cosine was square root of 2 over 2. Cotangent here is the cosine over the sine. So I could say cotangent of pi over 4 would be square root of 2 over 2 divided by square root of 2 over 2, which is just going to be 1. Okay. So the cotangent of 5 pi over 4, we were able to evaluate that just using the fact that the period was pi. Cosine's kind of similar here. This is an even function, so this is going to be the same as the cosine of 9 pi over 4. Remember, we can change that from negative theta to positive theta or vice versa for even functions. Well, the cosine of 9 pi over 4 should be the same as the cosine of 9 pi over 4 minus 2 pi, right? Well, that's the same as the cosine of 9 pi over 4 minus 8 pi over 4. Well, that's the same as the cosine of pi over 4. Well, we determined earlier that that is the square root of 2 over 2. Okay. Okay. So we're going to continue with this in the next section. We're going to talk about a different way of just kind of defining these trig functions. We're going to talk about some more special angles. The last thing I wanted to do very quickly was just to make sure on your calculator that you can solve this. Now, you are allowed calculators in class and on tests and things, but I did want to make sure you can evaluate things like the sine of pi over 4. And there's a couple keys here. First off, you will notice that this calculator is in degree mode. So if I want to find the sine of pi over 4, I either have to change pi over 4 to degrees, or I have to change my calculator to radian mode. So if I come to radian mode and I say, well, pi divided by 4, I would say this, and then if I want to find the sine on this calculator at least, I say trigonometry sine. So it'd be 0.707, blah, 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 blah. Which kind of makes sense because it'd be square root of 2 over 2. We should know, and we should be able to evaluate that, right? 2 square root. If I divide that by 2, I get 0.707. Okay. Now, the other way is if I'm just not real good on my calculator converting, I could always say, well, pi over 4 in degrees, if you go back, multiply that by 180 over pi, you would get 45 degrees. So if I take trigonometry, sine of that, same value. So sine of pi over 4, though, you should get 0.7071, I think. Yeah, 06. Blah, blah, blah. Okay. So just verify that you can do that on your calculator. There will be the case where you need to find. So the next one says cosecant of 1.5. Now notice there is no degree symbol there. So even though there's no pi here, I'm going to assume that that is in radians. So if I go to my calculator, the way you're going to do this, most of your calculator, now this one does have these buttons. Most of them, or a lot of calculators, do not have secant, cosecant, and cotangent buttons. So the way you have to find that, let me make sure I'm in radian mode again. So I would say, well, 1.5, I can't necessarily find the cosecant. I can here, but if you can't, I say, well, the sine of that is this value. Well, cosecant is the reciprocal of sine, so if I take 1 over that, I get 1.003. So that's one way you can find those alternate functions here. Okay, so I'm going to wrap it up a little bit quicker than last time, not a lot, so at least you have an overview of this section. I'm probably going to do at least one more to have ready for next week when I'm going to be out. But I wanted to make these available. We'll go over the homework sections. We'll go over a lot more details in the class sessions. If you have anything, any questions, or you're not sure on something, check the resources online and please just let me know and I will be happy to try to get something to you. But I believe that's it for this section. I hope you're having a good week and I will see you next time.